Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the next summary in the Padisco Introductory Statistics video series. In this one, we're going to talk about estimation. In particular, we'll be going over the philosophy of estimation, the methodology of estimation, the confidence interval for the mean, and the confidence interval for the proportion. Statistical estimation is one of the major fields in statistical inference. As we've talked about in earlier videos, we are inferring when we try to draw conclusions about a population based on what we know about a sample. And estimation is one of the main ways we can do this. Let's start with the philosophy of estimation. When we estimate, that basically means we are providing a range of potential values for a population parameter based on a single value that we've measured for a sample statistic. This range of values is known as a confidence interval. And as the name suggests, we have some level of confidence that the population parameter is in the interval we end up constructing. The level of confidence is usually expressed as a percentage, like 95% for example, and it represents how sure you are that the interval does contain the parameter you're trying to estimate. So let's look at an example. We all probably watch too much television, but how much on average do we watch each week? A sociologist conducted a survey of 25 people and found that the surveyed people watch an average of 27.6 hours. Now, when the sociologist tries to infer something about the larger population, what they can do is use this sample mean of 27.6 to estimate the true population mean. The true population mean is probably not 27.6 exactly, and the estimate will involve coming up with an interval of values centred on 27.6, and the sociologist will claim that they are somewhat confident that the actual average number of hours is somewhere in that interval. That's why we call it a confidence interval. But how do they work out what the interval is? Well, the middle of the interval is always going to be the sample mean. And the size of the confidence interval around this middle is determined by three things. First, how confident you want to be in the estimate. The more confident you want to be, the wider you're going to have to make the interval. Secondly, the standard deviation in the underlying population. Big standard deviations mean samples will vary more from the population mean, and so this will cause a wider interval as well. And finally, the size of the sample you collect, because the bigger the sample, the better it will behave, and so you can actually make a smaller interval estimate in that case. But exactly how do these things we just mentioned affect the size of the interval? Well, to see that, we turn to the methodology of estimation. It all comes down to sampling distributions. Let's keep looking at this TV example. We have a variable x, the number of hours a person spends each week watching TV. We want to construct a 95% confidence interval for the population mean, mu. We have a sample mean of 27.6 in a sample of 25 people, and let's assume we know that the population standard deviation is 10 hours per week. Think about the following reasoning. We know from what we've already learnt about sampling distributions in previous videos that whatever mu is, the sampling distribution of the mean, x bar, follows the normal distribution with a mean of mu and a standard deviation that turns out to be 2. We also know, because of what we've learnt about normal distributions, that 95% of all values in x bar will fall within 1.96 standard deviations of its mean. In simpler language, this means that for 95% of all samples we could collect, the true population mean mu will be no more than 3.92 from the sample mean. And so let's assume that our sample mean, 27.6, is one of these 95%. And 95% of the time, we would be correct in making that assumption. So we think that the true population mean, mu, is within plus or minus 3.92 of our collected sample mean of 27.6. So the confidence interval is 23.68 up to 31.52 hours. And this is our 95% confidence interval. Now we'll actually finish this example off by going to the next section, the confidence interval for the mean, because frankly that's what we've been looking at so far anyway. We just saw the basic methodology of constructing a confidence interval, but let's be a bit more precise about it now so that we can see generally how to construct it and the different factors that affect what the interval is. Like we've been doing with the TV example, we're going to assume that we know the population standard deviation, sigma. We've been assuming that it's 10 hours. Now, the assumption that we know sigma is not terribly realistic, but for the purposes of this summary video, it will do. In the Padisco Introductory Statistics textbook, we do go into great detail about what to do when we don't assume that sigma is known. So go there if you want to learn more about that. But to get back to the TV example, we were just seeing how the sampling distribution helped us construct the confidence interval. But you might have noticed at one stage we used the rather handy fact that 95% of any normal distribution lies within 1.96 standard deviations of its mean. This is a pretty common fact about normal distributions, but what do we do if we want to use some other level of confidence? Well, to address that, we have to relate the sampling distribution to the standard normal distribution, z. If we express the level of confidence like this, then there are two values known as critical values, denoted by z sub alpha on 2 and minus z sub alpha on 2. And these two values are actually z-scores from the distribution z, and they contain the percentage level of confidence in z, whatever that level is. So far we've looked at 95% confidence, and the critical values there are plus or minus 1.96. But if we wanted to have a 99% confidence interval, for example, the critical values would be further apart, plus or minus 2.576. Now, once we've got our two critical values for our confidence interval, we can write what the interval is down. Remember the TV survey, we took a sample of 25 TV watching times and we got a sample mean of 27.6 hours. Let's say we want to construct a 99% confidence interval, giving us the two critical values plus or minus 2.576. And we're assuming that the population standard deviation is known to be 10 hours. The formula for the confidence interval is given here. Plugging the values in gives us the interval between 22.448 and 32.752 hours. Notice the interval is centred at the sample mean, and the size of the interval is determined by how big or small this term is. In fact, this term is so important that we give it a name, the margin of error. So in a very generic sense, the confidence interval is given by this simple formula. Of course, the term E in that formula, the margin of error, contains a lot of the information in the confidence interval, and that margin of error is affected by three things. First, the level of confidence. A bigger confidence level will mean a bigger critical value, causing a bigger margin of error. Second, the population standard deviation. A bigger sigma causes a bigger margin of error. And finally, the sample size. Because n is in the denominator, a large sample size produces a smaller margin of error. And that's why, mathematically, the three things have the effect on the confidence interval we were mentioning before. Now that we've covered the mean, we'll look at the other major parameter we like to estimate, the proportion. When we have a categorical variable x and we're interested in a particular category in that variable, we might want to estimate the proportion of values that fall into that category. For example, let's say a sports fan is interested in studying left-handedness in baseball pitchers. So the variable is which hand a pitcher favours, and this has two categories, left hand and right hand. The fan is interested in what proportion of pitchers favour the left hand, and he wants to construct a 95% confidence interval. Let's say he manages to get his hands on some data for a sample of 100 baseball pitchers, and the proportion of these that are left-handed is 27%, or 0.27. Similarly to when estimating a population mean, this sample proportion, p, will form the centre of the confidence interval for the population proportion, pi. In fact, the formula for the confidence interval is given here. The symbols in this interval are the same as the population mean. For example, the fan wanted to construct a 95% confidence interval, and a little bit of maths shows that this would be the set of values from 18% to 36%. We've now seen a range of confidence intervals. The best way to get used to them, however, is to practice constructing them yourself, and that is where the Padisco e-workbook can come in very handy. So let's see an example from there. In this question, the Cloak soft drink company wants to determine the proportion of people that favour their soft drink over their competitors. They ask 30 people and find that 21 people in this sample prefer Cloak. They want to construct a 95% confidence interval for the population proportion. You can answer this question by dragging the two coloured dots onto the number line to indicate the lower and upper bounds of the interval. I'll do that now. And we get feedback for our answer and a detailed explanation of how to do the question. So that's estimation. The key topics were the philosophy of estimation, the methodology of estimation, the confidence interval for the mean, and the confidence interval for the proportion.